Start, sir.
Good afternoon, everybody. So, welcome to the first session of the course Introduction to Automata Language and Computation. So, we are at the sixth lecture, sixth week of this course, and today we are here to clear your doubts up to how much we have covered. So, just to recap, how much we have covered. So far we have started with the DFA, deterministic finite automata. So there we know this, it is a five tuple. One is the set of states, which is finite because we are talking about finite state machine. And then we have a symbols, so sigma, which is the alphabet, which is written on the tape, and we need to read that symbols. And then we have this state transition function, which is a function which takes one input as a tape symbol and another input as state. So our system is at some state, and depending on the input symbol, it will go to the another state. So basically that delta is a function from q cross sigma to q. So it is our system is at a certain state, and we take the input, we read some symbol on the tape, and then we will go to the different state. So that is the state transition function. So every automata has a state transition function, and then we have a state q0, which is called starting state, because our system has to start from some state, that is the starting state, that is q0. And we have some set of states, which is final state. It could be one, it could be more. Uh, that is the acceptance states of. So that is a subset of this capital Q. So capital Q is the set of all states, which is finite. So then we extend this delta for string. Suppose string is nothing but the symbol, the consecutive symbols of the input symbols. So then how we can take this input? So for that we have extended our delta to delta hat. So delta hat is basically takes the string. So string. So if x is a string, then x we can write the w a. A is a symbol. So it is a recursive definition. So delta of delta hat of q comma x is nothing but delta of delta hat of q comma w. So it's a recursive definition. We can start with from one symbol, then two symbol. Basically we are reading we are at some state q, then we read the symbol, and it will go to the another state, we will read the next symbol, sequential reading. So we are just scanning the tape. Our symbol, our string is written on the tape, and we are just scanning the tape. So that is the idea. And then if we reach to a final state at the end of this string, then we say this string is acceptable by our automata. So this string is accepted by our automata. And if we get this collection of the string, which is the set of all string which are acceptable by this finite automata, that means delta hat of q0. Q0 is our starting state, comma that x is the string coming from sigma star. The sigma star is basically the collection of all possible string. And then if delta hat of q0 and x, if it is reaching to the final state, then we say that is accepted. So basically this state, the language of this D, if our D is the deterministic finite automata, so L of D is basically nothing but set of all string x, such that delta hat of q0 comma x is a final state. Basically it belongs to F, capital F, which is a set of all possible final state. So 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 that is the L of D. So that is the language accepted by this DFA. Now the question is, we define a regular language. Then we define a regular language. So regular language is basically the set of all possible strings for which we have a DFA which accept this language. So any language we call regular if we have a set of string, if there is a automata which can accept this language. So then we say that language is a regular language. So then we have defined the NFA. So this is the deterministic finite automata. That means our delta is moving to delta is going to some particular state, deterministic way. Now there is a NFA, non-deterministic finite automata. There we have an option for moving to different state. So from a given state, if we read a symbol, then we can go to different. There is a option for going to different state. It's not deterministic. It's not. That's why it is called non-deterministic finite automata. So in that case, also we extend the delta to delta hat. So only difference from NFA and DFA is the state transition function delta. So here earlier the delta was mapped to a particular state, but here we have an option. We can go to so that depends on this delta function. We can go to different states. So the range, the domain of the this delta is then the power set of this Q. Q is the capital Q is the set of all possible state. That means it is a subset of. So it can go from a given. So delta of Q comma A is a symbol and small q is a state. It is a subset of capital Q. So we have a small set. So it can go to different state. So that's why it is called non-deterministic. And then there also we have extended this delta to delta hat on the non-deterministic sense. Then we have a different path. Then we define the language. Language means accepted by that NFA. So we define L of n. That is nothing but if we start from a Q0 and then if one path, there will be many paths reaching to many different state. So if the one path is reaching to a final state, then we say that that string is accepted by this NFA. Okay. So then we have discussed that this DFA and NFA are equivalent, so they are accepting the same language, and then we define the epsilon NFA. So there we have discussed the epsilon move. Even without reading the symbol in the tape, our system can change the state. So there's few applications are there on this. So that is called epsilon move. We have more freedom. So our system can change the state even without reading the tape symbol. So that is called epsilon move. So here in this case we call that epsilon NFA. So the epsilon NFA is basically nothing but that that is also 5 tuple, but only thing we have a extra input which is epsilon. Epsilon input means we are not taking any input. It is a null input basically. So we are not reading the tape symbol. Still we can move to another state. So that is called epsilon move. So we have a epsilon move in this epsilon NFA. Other than that, everything is same. But here we have to be careful about the string accepted by this NFA, because then we have defined the epsilon closure. Because when you read a string, so even if we read a symbol A, one tape symbol alphabet, then also before that we can have a epsilon move, and after that we can have a epsilon move. So that way we can define the epsilon closure of a state. That means with only epsilon move where it can go. So that depends on the state transition function given for that epsilon NFA. And in the lecture we have taken some example where it was more clear to by through example we have explained that how this epsilon closure are can be constructed. So because if we take a symbol, before that there is a epsilon, after that there is a epsilon. That means we have to consider the epsilon closure on that state where we are, and then after taking A, we are going to some other state. From that state also we need to take epsilon closure. So that will be basically delta hat of q comma A. Even it will be little more rigorous when we talk about the string, because in string also we need to keep in mind of the this epsilon closure, because by through epsilon move without reading the tape we can go some different paths. So that is also need to keep in mind. So there we have discussed that epsilon closure. I mean the epsilon NFA, NFA and DFA all are equivalent. So they are basically accepting the same language. So basically the regular language is a language which can be accepted by any finite automata. Either it is NFA or DFA. If it is accepted by epsilon NFA, then we know, we have proved in the class, then we have a equivalence NFA which can accept that language. And if we have a NFA, we have proved that we have equivalent DFA. Basically, we are merging that state to make a subset of a state. We define the another state for the DFA. So that proof we have discussed in the class. And so the regular language means it has to accept by a finite automata, either NFA, because NFA accepting by a epsilon NFA is very easier to see, because there we have a freedom to use the epsilon move, because that will help us to do this. Okay, so now the question is, there we have discussed in the regular language we have discussed also regular expression. So then we have seen that every symbol can be expressed as a single set. Then we have defined the regular expression as a plus symbol dot concatenate symbol. That is plus means it is a union of that L1 and L2. So regular expression also we have discussed, and we have seen the equivalency between the regular expression and finite automata. Then in the 6th week lecture, which is currently is going on, so there we have talked about very important theorem, which is called this pumping lemma, which is a necessary condition to show that a language is not regular. For example, if we consider suppose our symbols are 0, 1, our sigma is 0, 1, our alphabet is 0, 1, 0, 1, they are the symbols, tape symbols. Now, if you consider a language 0 to the power n, 1 to the power n. Okay, so the question is whether this is regular or not. So intuitively, you can think for this is non-regular, because to be regular, we need to have a finite automata which can accept this language. Now, if you see the string of this, it is 0 to the power n and 1 to the power n. So for some n, say n is 2020. Now, why we cannot have a finite automata for this? Because this is, look at the string, 0 to the power n, 1 to the power n. So that means number of zeros should be same as followed by the number of ones. Now, finite automata has no memory. So we will count for us, how many zeros we have read in the tape so far. Then we can, when we start counting so there is no way we can have so memory, it has no memory basically. So our finite automata has no memory. That is the main reason that we cannot have a automata for this 0 to the power n, 1 to the power. Even we have proved this by using the pumping lemma, that 0 to the power n, 1 to the power n is not a regular language, but it is a context-free language. We will discuss in later stage that context-free language, for that we need to have a context-free grammar. Then after that we will discuss the push down automata, because there we can introduce a stack, the memory, so that we can count how many zeros we have encountered. Then we can count how many ones we are encountering. So that way we can just accept this 0 to the power n 1 to the power n. So we need to have a memory. So that will be that stack can help us. So that we'll discuss in the push down automata. But this for finite automata, I mean this automata DFA, NFA, epsilon NFA cannot accept this 0 to, because we cannot use there is no memory in our this automata. But yes, we can have a grammar for this. So that is a context free grammar, and we can have a so this is a context free language. Okay, so that is the, so let me open some of the questions which you have posted in the Google sheet. So we have very yeah, one question is why we need extend transition function in NFA. Yeah, because unless we so delta is the transition function, yeah, NFA or DFA. So but if we don't consider delta hat, because ultimately our goal is to accept a string. So if we have to accept a string, we need to define the delta hat. Delta hat is basically we start from any state. So here to see this is whether this is an acceptance string or not, we need to start with the starting state Q0. So basically we want to see we put this symbol in a tape, that string, and then we start from Q0 and we read the string slowly one by one. That is basically delta hat. Delta hat of Q0 comma that X. X is a string. If it is reaching to some final state, then only we say that is the acceptance. That is the reason we need to extend this function delta to delta hat. I hope this question is clear. Okay. Yeah. Now another question is if L1 is a regular language, L2 is the context-free grammar, then which of the following is a context-free language? L1 in, yeah, that this thing we'll cover when we'll discuss the context-free grammar. So L1 intersection L2, L1 union L2 union, and L1 concatenated L2. This thing we will cover in the maybe after next 2 weeks, next week or so, next 2 weeks. So this will cover these things. Okay, and then another question maybe I can take from the YouTube. Yeah, so one question is the sir from DFA transition diagram, can you directly get the regular expression without applying the recursive formula? So add-ons method. Yeah. So this recursion formula help us to see, because maybe sometimes it's not very easy to construct directly that get the idea to get the DFA, but regular expression will help us to get the DFA. Yeah, so add-ons formula you can use for that. So how to prove that the given, another question is how to prove that the given language is regular or not. In general, how to apply pumping lemma for any language. Yeah, pumping lemma is the condition for a language to be regular. If it is not satisfying the pumping lemma, then we can say this is not a regular language. So we can just get a pump in the middle, then we can see whether that is accepting that. So if it is not, then it is not non-regular language. So Mythil Neora theorem, no, we haven't discussed. And in your picture of no, this is so. If you have any question related to the course material, then we can discuss course content. No, no further question. So okay, so maybe I can just talk about something on the coming week. Like we have after this, we'll discuss the context-free language. and then we'll talk about the context-free grammar, and there we'll see this 0 to the power n, 1 to the power n can be accepted by, we can have a context-free language which can accept this. So this is a context-free, sorry, we can have a context-free grammar which can accept this. So this is a context-free language. And then after that, we will move to the push down automata. And then, and there we'll see how we can have a memory there. So we will use stack there. Okay. So then finally, if time permits, we'll move to the Turing machine. So that is the, so both way we can read the tape. So we can write on the tape. We can basically, this is a finite state machine. So we everything we should be converted into this written in the string, in the tape. So we should end up with a acceptance things. So that is the idea. Any further questions? Yeah, if you have any question, you can post in the chat box of the YouTube link. I can't see any other questions. Yeah, so I think we can stop here if there is no further questions. And can see one question regarding the exam. So yeah, so uh, yeah, so assignment, if you are doing the assignment, you will get some idea of the, even there is a policy that some part of the exam question will be similar from the assignment, 30% or so. So I strongly recommend you to do the assignment honestly, so that you can get the idea of the exam paper. And as you know, all will be MCQ. Exam also will be MCQ. Okay, so I think we can stop here, because if there is no further question in the chat box, and maybe after 1 month, so we have a second live session, in which we can, after covering some material, we can again discuss your doubts, and then at the end we have a, if time permits, we can have a live session. Okay, so thank you. I'm closing the session. Good luck.